And 10 more seconds. And 3, 2, and 1. Okay, we're going for 1 as the most popular, but only half, so we're going to chat about that. And that means 2 of them are incorrect. So let's take a quick minute to review this concept. Okay, I have my magic hybridizer that I brought to class today. It is this magic cup that can hybridize atomic orbitals into hybridized orbitals. If you were here last Friday, you saw this. So if we want to make sp3 hybridized orbitals, if we need 4 regions of electron density, so the central atom has 4 atoms, or a non-bonding pair and 3 atoms, it has 4 regions of electron density. If we need 4 hybridized orbitals, that means we need to put in 4 atomic orbitals. We have the options of s, px, py, pz, and 2 d orbitals. We don't go to all 5 because it just gets way too big and we don't have atoms that have that many bonds. Okay, so if I need 4 hybridized orbitals out, 4 regions of electron density, I put 4 atomic orbitals in. So I start at s, p, p, and p. So I put in 4 atomic orbitals. I shake up my magic hybridizer, and out come 4 hybridized orbitals. These are 4 degenerate, so same energy, same size and shape. They have a big lobe and a small lobe. P orbitals have equal lobes, right? They're symmetrical. These are not symmetrical. 4 degenerate hybridized orbitals, and they're going to be oriented in 3-dimensional space as far apart from one another as possible, which tells us they will have a tetrahedral arrangement. So 1 orbital going here, and 1 orbital going here, and so on. If you look on your model kit, you'll see the label sp3 on these black prongs because this tetrahedral shape is made with an sp3 hybridized atom. So that's where we get our sp3 orbital. So that means sp3 orbitals are produced by the combination of an s and 3 p's. What do we call it? Well, we look at what we put in. S, P, P, and P. So we call it an sp3 hybridization. This carbon atom, if this was CH4, is sp3 hybridized. Each of the orbitals that are formed are sp3 hybridized orbitals. And I get 1, 2, 3, 4 sp3 hybridized orbitals out. So that one is correct. What about the next question? Or the third statement, let's look at that one. A central atom that is sp3 hybridized will have a trigonal planar molecular shape. And that's not the case because if we have sp3, that means we put in s, p, p, and p. That means we have 4 regions of electron density, and 4 regions of electron density tells us to start with our tetrahedral electron arrangement. Even if one of these was non-bonding, we're not left with a trigonal planar shape, we're left with a trigonal pyramidal shape. So we could be trigonal pyramidal if it was like NH3, for example, but we're not going to get trigonal planar from an sp3 hybridized atom. So the planar is the problem. If it said trigonal pyramidal, that could be an option. So that's wrong. This one's also wrong, and this one required some critical thinking. A carbon atom in a compound could be sp3d hybridized. Let's think about what that means. S, P, 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 and D. That means we put in 5 atomic orbitals to get out 5 hybridized orbitals. Each orbital can hold 2 electrons. 5 times 2 is 10. Can carbon have a valence shell of 10 electrons? No, it's too small. It's in the second period of the periodic table. So a carbon atom is never going to be sp3 dehybridized, because that means it could take on 10 electrons. If we go into the third row of the periodic table, like sulfur, we're getting into bigger atoms that can have an expanded octet. But carbon can't, because it can't reach into those d orbitals. It's just too small. So this wasn't in the notes per se, but we need to understand what that hybridization means, how it relates to electrons, and recognize that carbon is too small to have an expanded octet. Okay, so that is our crash review of hybridizations. So continuing on in valence bond theory, we're now going to discuss some implications of this theory based on those principles that bonds are formed by overlapping orbitals, that electrons are localized in those orbitals. That means they're not anywhere they want, they're sticking to those orbitals, and that atoms can hybridize and form these hybridized orbitals. So there are a few takeaways that are really important, a few implications that we get from valence bond theory that helps us to understand how bonding works. First thing is how a sigma bond is formed. And this was briefly mentioned last class, but now we get to dig into it a little bit more. A single bond is a sigma bond. You can almost use them interchangeably now that we understand valence bond theory. A sigma bond, by definition, is the overlap of orbitals on axes between the nuclei. So if we have two nuclei, A and B, the electrons or the orbitals need to be overlapping between those two axes, or between those two nuclei. So they're overlapping. If you drew a straight line between those nuclei, those electrons are hanging out between those two nuclei. This is called an on-axis overlap. Now we could have an overlap of an atomic orbital with an atomic orbital. So I brought my little red balls. If this was a hydrogen 1s orbital, and this is a second atom of hydrogen with a 1s orbital, we bring these into close proximity. The 1s orbital and the 1s orbital overlap, and they can form a sigma bond. If we imagine the nucleus in the middle of each of these, the overlap is occurring between the two nuclei. So this is a sigma bond. It could happen between an atomic orbital and a hybridized orbital. So here we have our CH4, our methane example. The carbon atom is sp3 hybridized, as we talked about last class. We have 4 regions of electron density. We put in 4 atomic orbitals. We get out 4 hybridized orbitals. So this is an sp3 orbital, and so is this one. And one of these sp3 orbitals overlaps between the carbon atom and the hydrogen atom. So the 1s atomic orbital of hydrogen and an sp3 orbital of carbon overlap on axes. So it's like they're overlapping between the axes, and we form a sigma bond. So each overlap is a sigma bond. So this compound has 4 sigma bonds. This could also happen by overlapping hybridized orbitals. So an sp3 orbital from one carbon and an sp3 orbital from another carbon could also form a sigma bond. Now in these hybridized orbitals, we could have bonding electrons, we could have non-bonding electrons, but when they overlap, that becomes a sigma bond. So now we get to the more interesting example of a double bond. A double bond is made up of a sigma bond, what we just talked about, and a pi bond. And we're going to introduce pi bonds from valence bond theory. So we're going to start with the example of ethene or ethylene. This is the organic molecule that's given off from fruit that's ripening and that helps the fruit to ripen more. Now we're going to start with the sigma bonds. So we have the Lewis structure on the left, And then we have our hybridized orbital picture on the right. I'm going to start on the left. The carbon atom on the left has 3 regions of electron density: a single bond, and a double bond. So 3 regions of electron density. That means it has 3 hybridized orbitals. What went in to make that? Well, an S, P, and P. So this carbon atom is sp2 hybridized. The one on the right also has 3 regions of electron density, and it is also sp2 hybridized. So carbon 1 has 1, 2, 3 sp2 hybridized orbitals. So the carbon atom is sp2 hybridized. And the one on the right is also sp2 hybridized. And when the sp2 hybridized orbital overlaps with one of the 1s orbitals from hydrogen, we form a sigma bond. And we can count the sigma bonds. 1, 2, 3, 4, 5. 5 sigma bonds in this ethylene molecule. So far, we've just looked at the sigma bonds. Now, you know what? I said a moment ago that all single and sigma are almost interchangeable, and that was inaccurate. I need to clarify that statement. A single bond is a single bond, bond order 1, is a sigma. A sigma is not always a single bond. Okay, so a sigma makes up a single. A sigma also contributes to a double bond. So we have the sigma bonds taken care of. We have a single bond between each hydrogen and carbon. We don't have a single bond between the carbons, though. We have a sigma, that cool little symbol, but we also have something else happening. Where did these sp2 hybridized orbitals come from? Well, as we just mentioned, we pulled in an S, a P, and a P. Did we pull in Px, Py, or Pz? Well, it kind of depends on what vectors, what orientation you're considering. In this diagram, we're pulling the atoms together along the x-axes, so it is important that we pull in the x and the y. These 3 atomic orbitals were hybridized in the magic hybridizer to make 3 sp2 hybridized orbitals. 3 regions of electron density, oriented as far apart as possible, makes a trigonal planar shape. But most importantly, for the purpose now, one of the p orbitals, the pz orbital, was not hybridized. It remains as a pure atomic orbital, not hybridized. It's still just hanging out as a pz orbital. And now this comes into play and it becomes important. So I'm going to pull up my little model kit over here, and you have this in your model kit as well. So I've pulled out this double bond piece, and you have a couple of them in your kit. And then I pulled out 2 gray pieces. They kind of look like the black ones, but these ones are labeled as sp2 hybridized. So you would expect the bond angle here to be 120 degrees rather than 109.5. So they're labeled as sp2. And my hydrogen atoms, I'm representing with these red balls. So I've made my ethylene or ethene molecule. Now, so far, we've identified the sigma bonds. This is a sigma and a single, here, here, and here. And so far, we know we have a sigma. The sp2 hybridized orbital from this carbon and the sp2 hybridized orbital from this carbon have overlapped on axes between the atoms to make that 5th sigma bond. But each of these carbon atoms also has a p orbital. So now, remember, we're working in 3-dimensional space. I'm going to take this molecule and tip it up like this, because the pz orbital, let me make this any taller. The pz orbital is orthogonal to the plane of the molecule. See how this molecule lies nice and flat? If I bring it up, you can imagine it's like a sheet of paper. The pz orbital lies orthogonal to that plane. So it's perfectly up and down from the rest of the molecule where all those sigma bonds are. Each of these carbon atoms, the one on the left and the one on the right, each has a pz orbital that was not hybridized. So it still looks like a pz, right? Like the dumbbell shape, one phase up, one phase down, and so on. Now, these p orbitals can overlap above the plane of my molecule and below the plane of my molecule. So the pink ones overlap and the blue ones overlap. And this makes a shared electron density region above the plane. It's kind of hard to hold in place. Above the plane and below the plane. This shared electron density region up here and down below makes one pi bond. A double bond is the sigma direct overlap and the pi. The pi is not a direct overlap. If I was trying to do a direct overlap like the sigma, if this is my finger is pointing to the nuclei right here, I bring them together on axes, that's a sigma bond. But if I bring them side by side, this makes a pi bond. See how it's not overlapping between the axes? It's not overlapping on axes. It's a side by side overlap, and this makes a pi bond. So let's see if we can draw that on our paper now. We have the 2p. We can call it z because we've defined this direction as x. If you wanted to define the direction as z, then you combine a different one. But for our purposes, we'll say it's this way. So we have an overlap above the plane, an overlap below the plane. And if we take that sigma and the pi, because we have that sigma on axes overlap, that's what makes a double bond. Now, if I go back to this molecule here, this double bond cannot rotate. Your model kit is nice because if you try to rotate this, you can't rotate it very much. This restricts rotation. Why? Well, if I try to rotate this pi bond, that's exactly what happens. It breaks. It's held together because of this shared electron density region between the pink and the blue. But if let's see if we can look at it this way, rotate it, that shared overlapping literally breaks and falls apart like it just did here. So that's why double bonds can't rotate. When they rotate, we break the pi overlap, which is why we can't rotate it. Okay, so this picture is just showing you different visualizations of this overlap region to make one pi bond. We have a shared region above and a shared region below. And then if your eyeball was looking down the carbon-carbon axes, that's the picture that you get here. So again, going back to my toys over here, the middle picture, I'll go like this, so the blue's on the top. The middle picture looks like this. The picture on the right just means we're looking down the carbon-carbon axes. So you can just see the blue electron region above and the other phase below. It's just another way of looking at it. And then we have this masterful picture at the end showing all 5 sigma bonds and the 1 pi bond. Super. Okay, I'm going to walk around with this just so you can visualize it a little bit more. When we try to rotate this double bond, or rotate this pi bond, that's going to break the overlap. And that's why double bonds don't rotate, which is why we have a whole topic coming up on isomers around double bonds, because they can't rotate. And we end up with a whole classification of molecules called cis-trans isomers, because whether one group points up or down, whether it points with another interesting group or away from another interesting group, that makes a different molecule. You can't just rotate them to make them the same. They're different molecules, and we need to be able to distinguish them. So that's how cis and trans molecules arise. We're going to learn how to identify and distinguish between these molecules coming up in a later topic. Okay, so we've looked at double bonds. Now we need to go to triple bonds. So that means we're going to start with sp hybridized orbitals. So this is a slide from last class. How do we make sp hybridized orbitals? Well, we put in an s orbital and a p orbital, 2 atomic orbitals in. You shake up your magic hybridizer, you get 2 hybridized orbitals out. They orient themselves as far apart from one another as possible, which gives you a linear structure. Important for today, that means we have 2 p orbitals that are left that are not hybridized, that remain as pure atomic orbitals. And these are the ones that can participate in pi bonding. So let's now look at acetylene. So C2H2. We have carbon 1 and carbon 2. Each of these carbons is sp hybridized. So here's one of the sp hybridized orbitals and the second, and then for the second carbon, an sp and another sp. The overlap between the hydrogen and the carbon makes a sigma bond. The overlap between the sp and sp of 2 different carbons makes a sigma, and then another carbon-hydrogen bond makes another sigma. So we have 3 sigma bonds from the direct head-on overlap. So if I had, let's imagine this lobe is really small, but I'm bringing these together. This head-on-head overlap, imagine that it kind of smush into each other. That becomes a sigma bond between the 2 carbon atoms. That takes care of the sigma, but then we have the py and the pz. So I'm going to pull out now this triple bond. So you have this in your model kit, and it represents a triple bond. So we have carbon atom here, another carbon atom here, and then my 2 hydrogens on the end. Between carbon 1 and carbon 2, we have this triple bond. And it's kind of funky to look at because you can see it kind of has an X, and it's representing the 2 pi bonds. So this carbon here has a p, y is going up and down. So let's say y right there. And this carbon here also has a pz. Now imagine these perfectly overlaying. So this one, it's getting really messy, has a py and a pz. And the one on the right has a py and a pz. And the ones that are both straight up and down can overlap, and the ones that are side to side overlap. So we have a pi bond forming front and back, and another pi bond forming up and down. So the overlay of the top and the bottom, that makes a pi bond. And the overlay of the front and the back, that makes another pi bond. So we have 2 pi bonds, and we have our sigma bond. 1 sigma, 2 pi makes a triple bond. So we have different ways to visualize this. I think it's really helpful to play with the model to be able to visualize how we have overlap this direction, straight up and down, how we have overlap straight towards you. Those are our 2 pi's, and then we have sigma overlapping head on head. Okay, so let's do some examples now. We want to determine the number of sigma and pi bonds in nitrogen. That's where we're going to start here. So first step is to draw the Lewis structure. We've already covered that, so I have simply provided it for you. Well, nitrogen number 1 has 2 regions of electron density. Now you can see why we use that somewhat vague term of region of electron density, because it could be a single bond or a double or a triple. We're really narrowing in on that sigma bond. We have an sp orbital here and an sp orbital there. So the nitrogen, we say, is sp hybridized. And it's overlapping with the second nitrogen's sp orbital, and then a non-bonding pair of electrons is in the other p. So that overlap there is our sigma bond. So we have one sigma bond. And now, frankly, it just really gets messy. I don't know if there's a way around this. We have, if it's combining along the x-axis, then each of these has a py or a pz, whichever direction you want to show. That overlap is giving us a pi bond. And then coming out at us and going away from us, you can see how it's getting really messy, out and away. That overlap makes a second pi. So we have one sigma and two pi. And that's how we get our triple bond. So I'm going to leave that one up on the screen. Good luck with your 3D imaging on 2D paper. And my question for you is, how many sigma and how many pi bonds are present in acetone, which is often used as a nail polish remover? Chat with the person beside you and count them up. It's really hard without colors.
And then I tried to the high bonds.
It's tricky because it's above. And 10 more seconds. And 3, 2, and 1. Okay, 3/4 going for A, and I agree. We're going to count up the sigma bonds to start. Notice that I drew in the single bonds between carbon and hydrogen because I can count them more easily. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That double bond is a sigma and a pi. So 9 sigma and then 1 pi. And that wraps up 3.4. And at this point, we're like, awesome. We know how to draw Lewis structures, identify bonding and non-bonding electrons. Awesome. We know how to go to 3.2 and take Lewis structures and turn them into 3-dimensional structures using VSEPR theory. And 3, 2, and 1. So that preamble was actually important. So Lewis structures, yay. We moved to VSEPR shapes, yay. We moved to valence bond theory with hybridized atoms. We figured out pi bonds, yay. So the big question is, Why the heck is there another theory? We've sorted everything out, right? We figured out shape, we figured out electron regions, we figured out pi bonding. Unfortunately, there are still a couple issues that we have with bonding. One issue is resonance structures. Valence bond theory that we just looked at takes a localized approach. That means the electrons are hanging out exactly in the orbitals where we put them. But how do we explain resonance structures then? We could draw the Lewis structure on the left, we could draw the Lewis structure on the right, but we know that the resonance hybrid is a more accurate representation. The carbon to oxygen bond order is 1.5. It's not 2 and 1. Those are valid Lewis structures. Keep drawing them like that. But it's actually a 1.5 bond order, not 2 and 1. Valence bond theory doesn't account for that because it says the electrons are localized. So they're in the double bond or they're in the single bond. That's it. The example that you have in your notes is the benzene molecule, where it's double, single, but it's a resonance structure. Those double bonds could equally be written in different spots. More accurately, we draw the resonance structure with the circle in the middle, showing it's double, single. Valence bond theory doesn't explain that. Okay. Next problem. Valence bond theory doesn't tell us, and Vesper and Lewis, don't tell us anything about the relative energies of electrons. You're like, well, I don't care about the relative energies of electrons. Why do we care? Well, it depends. It impacts color. It impacts reactivity. Electronic transitions, we know from fireworks and atomic theory, is important in color and absorbing and releasing energy and excited states. So we do actually need to know about those electronic transitions and the energy of the electrons in the structure. So we don't have anything to go on. And what we've learned so far, Lewis structures, Vesper theory, valence bond theory, doesn't explain a really interesting phenomenon called paramagnetism and diamagnetism. Diamagnetism, imagine something dyed. It is a substance, a material, that's not attracted to a magnet. Why? Because all the electrons are paired, so there's no net attraction. That's in contrast to a paramagnetic species that is attracted to a magnet. Why? Because it has an unpaired electron in an orbital. Why do we care? Well, it's giving us information about how the material is going to behave, and it also tells us whether the electrons are paired or not and what orbitals they are in. And Lewis structure, Vesper theory, valence bond theory doesn't help us to accurately predict paramagnetism or diamagnetism. For example, oxygen, we would draw this Lewis structure. Please keep drawing this Lewis structure. This is the correct Lewis structure, but it shows all the electrons as paired. Guess what? They're not. Oxygen here is actually paramagnetic, and we're going to watch an experiment demonstration showing this phenomenon. So what we're going to do here is watch a couple-minute video, and we're going to be comparing nitrogen, N2, triple bond, lone pair of electrons, and oxygen, lone pair of electrons, double bond. One is paramagnetic, one is diamagnetic. Our Lewis theory predicts that all the electrons are paired, but that's not the case. So we want to observe this phenomenon and then find out what to do about it. So we're starting with pouring some liquid nitrogen. It is very, very cold. It boils at -196 degrees Celsius. So if it's liquid, it's like -200.
This oxygen gas,
pass it through
this copper coil
that's immersed in liquid nitrogen.
Sorry, I'm
going to start that once more. I was talking. Can you imagine talking during a movie?
So we're going to
this oxygen gas,
pass it through this copper coil
that's immersed in liquid nitrogen.
Liquid nitrogen will condense the oxygen into liquid oxygen, which will collect in this pre-cooled dewar. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also through the poles of the magnet. And then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
The liquid nitrogen is very, very cold. It's so cold it can turn oxygen gas into oxygen liquid. The heat from that oxygen gas is coming off as it condenses to a liquid. And we can see the oxygen liquid collecting over here. This is colder than negative 180 degrees Celsius, so probably like almost negative 200 degrees Celsius. So that's the air we breathe, so cold with the liquid. Now this is liquid nitrogen being passed over the poles of a magnet. Notice how the liquid nitrogen just flashes right through that magnetic field. See how the liquid oxygen is attracted to that magnet. It's hanging out between the poles of the magnet. It's behaving differently than the liquid nitrogen. Okay, so this experiment tells us that oxygen is paramagnetic. It is attracted to a magnet. That means it has unpaired electrons, which is not predicted by Lewis or valence bond theory. So that big preamble tells you why we need to have another theory. And this is the final theory that we're going to do in chapter 3. So molecular orbital theory. Again, looking at that title, we're now looking at the entire molecule. Remember how we counted up all the electrons in a molecule for Lewis, even though you could have just drawn lines between the dots? We want to take a whole molecule approach. Rather than looking at atomic orbitals, s, p, d, f, that just belong to that atom, we're now looking at molecular orbitals, orbitals that belong to the whole molecule. Molecular orbital theory. This goes back to electrons behaving as waves, and we need to remember what those wave conditions are. Item 1, electrons are delocalized. That's direct contradiction to valence bond theory, where electrons were localized and stayed where we put them and hung out right between those two atoms. Now, I will say, we taught you Lewis, Vesper, valence bond, because they're still good theories. They do the job they were intended to. Lewis still helps us get to bonding and non-bonding electrons. Vesper still helps us get to shapes. Valence bond theory still helps us explain shapes and pi bonds. So it's still good stuff. We're going to keep some aspects of that, but they're just incomplete. So keep using the theory that's simplest. You don't have to jump to molecular orbital theory if you want to draw the structure of NH3. But we need the more complicated, wholesome theory to get to colors and other important molecular properties. So now electrons are delocalized, they belong to the whole molecule. These orbitals that we're going to be investigating have quantized energy levels, and they're different. So it's level 1 or level 2 or level 3, and we can compare which orbital has higher energy and lower energy. Kind of like SPDF, we knew the patterns. We're going to learn the patterns here. They have quantized energy levels. It can be this or that, but not in the middle. And we're going to be able to explain paramagnetism and dimagnetism, because we can now, using this theory, accurately predict if electrons are paired or not paired. It's treating electrons as waves. What do we need to remember about waves? Well, waves have a positive and a negative phase as they go up and down. Remember how I said it's not a charge, it's not a positive charge or a negative charge, but it becomes important later? Now's when it becomes important. Whether we're combining positive phases to make something more positive or negative phases to make a node, those matter. Waves have constructive and destructive interference. We can add and subtract, and they do different things. That matters. And we can remember there are nodes with electrons as waves and waves. There are going to be nodes in our molecular orbitals as well. So we're going to start with the simplest example. And this is constructive combination of 1s orbitals. So I have a 1s orbital from one hydrogen and a 1s orbital from another hydrogen. And as I bring them in closer proximity, they're going to form a new wave function. They're going to form a new orbital. We started with a 1s and a 1s. And I'm going to bring them closer together. This kind of reminds you of valence bond theory, right? They're bringing closer together to have shared electron space. But as we bring them closer together, we can now draw them closer together. We can mathematically add these two wave functions. So I'm going to add the high part here at nuclei 1 and the high part here at nuclei 2. And then when we add this part and that part, that's going to sum, it doesn't perfectly sum up to that, but we're going to sum up all of these pieces and see that we have a positive phase. We now have a new orbital that we have formed. And the naming system for these orbitals is important. Everything tells us something. Here, we are bringing these two nuclei, or the two orbitals, I should say, together on axes. We're combining them. If we drew a line between the two nuclei, we're combining them along that line, which means on axes. That tells us it's a sigma bond. Just like valence bond rules, when we bring a sigma bond, this is a sigma orbital. They came from 1s atomic orbitals, so we call it sigma 1s to remind us of where this new orbital came from. This is constructive interference, meaning it's producing a successful bonding region. That's in contrast to a destructive combination or an anti-bonding orbital. Let's imagine that I have one hydrogen atom, and now I'm combining the negative phase of the other atom. So I'm adding the positive and negative phases together, or the way that's expressed in your book is we are subtracting them. So we're taking the two positives and subtracting them. So we have a positive phase and a negative phase, and as we bring them into closer proximity, we again can add up those regions, but it ends up that the positive phase and negative phase don't interact well together. They have destructive interference, so destructive that they form a new node between the two atoms. Destructive interference or destructive combination, because when electrons are in this anti-bonding orbital, it's destroying the molecule. There's a new node. The electrons in this orbital are hanging out away from these atoms, not pulling them together. So if electrons are in this anti-bonding orbital, their presence is actually tearing this molecule apart. The name matters. Sigma, because we're combining them on axes. 1s, because it tells us where it came from. But now this destructive combination gets a little star, and it's called anti-bonding. So look at the difference. Constructive interference, bringing them together to make a bonding orbital, a sigma 1s bonding, versus a sigma 1s anti-bonding, or a sigma star. We're going to pick up from here on Friday and see how all these pieces come together. Have a great day, and I will see you on Friday.